This is the first video in chapter 2. So we just finished chapter 1. And in chapter 1, we ended the chapter looking at significant figures and all of those lovely rules and dimensional analysis. So we were using our calculators a lot. So I don't know if this is good or bad news, but we're not going to be using our calculators very much in chapter 2. We're kind of taking a break from the calculation side and moving on to the more conceptual side. There's definitely lots of material in chapter 2. It's actually one of our longest chapters, but there's not that much math. I'm not saying none. You will use your calculator some. But I like to preface this chapter with just letting everyone know that even though you won't be doing a lot of math in chapter 2, that sig fig and dimensional analysis stuff from chapter 1 is super important, and it comes back with a vengeance in chapter 3 and pretty much the rest of the semester. But what this lets you do is if you struggled at all with the sig figs and the dimensional analysis, you'll get a chance to kind of keep working through that so you can get comfortable with it as you also work through chapter 2, but we're not throwing more math on top of you right away to give you a chance to ask me questions and to practice problems. Okay, so that's the background stuff. Now we're going to actually start chapter 2. So we're going to begin by talking about an atom. Atoms are that's one of the words. Oh my gosh, I'm having problems with words today. I'm so sorry. We defined an atom in chapter 1. In chapter 1, every image that I showed you with an atom was a sphere with a different color. So atoms are usually represented by textbooks and chemists as little spheres, as little balls, and then they're different colors based on what element they are. Okay, so we're going to look at the history of an atom. When did someone first decide atoms existed, and then how has it evolved? Okay, so we're going to start with first some laws that are going to be important for us. So we talked about laws in chapter 1. So laws come at the end of the scientific method. Many people have done many experiments to prove these, and laws are just statements. They don't explain how or why. They just say what is. Okay, so this first one is the law of constant composition, which is also called the law of definite proportions. That's why I have both terms there, because it's the same thing. And it says that the elemental composition of a pure substance never varies. So pure substances, we also talked about those in chapter 1. There are two types of pure substances. There are elements and there are compounds. So if something has been considered an element, the composition of the elements inside of it never change. And if something's considered a compound, then the composition of the elements inside of it also never change. And to be more specific, it's not just, oh yeah, this compound is made of carbon and oxygen, but how many carbons and how many oxygens are in each molecule of that compound. Okay. So if I have a molecule that has 1 carbon and 2 oxygens, that's a pure substance. But then if I have another molecule that has 1 carbon and 1 oxygen, that's also a pure substance, but if they're in the same container, I've now made a mixture because those are two separate pure substances. The law of conservation of mass is specific to chemical processes. For us, every chapter, every example we're going to see in this semester is going to be a chemical process. In chapter 1, we talked about chemical changes and chemical properties. So a chemical reaction is just a chemical change. So the law of conservation of mass says if at the beginning of a process, before you've done your chemical reaction, measure out the mass of all the things that are going to react. Okay, write that down. Then the chemical reaction happens. The chemical process happens. The mass at the end will be exactly the same as the mass at the beginning, which is saying when a chemical reaction happens, matter is not being created or destroyed. We're not making new atoms or destroying atoms. What's happening in a chemical process based on this law of conservation of mass? I think of it like Legos, because Legos are fun and everyone loves Legos. That might not be true, but I love Legos, so that's important. So if I had a bunch of Legos and I used those Legos and I built a house out of those Legos, that would be like my reactants, what I'm starting with. And then I took apart those Legos and put them back together and I made a boat using every single Lego that I started with. Wouldn't the mass of the house and the mass of the boat be the same because they were made up of the same Legos? Well, if those Legos were each atoms, that's an example of what a chemical process is. When a chemical process happens, we're not making new atoms or destroying atoms, we're just putting them together in a different way. So that's why the law of conservation of mass is true. All the pieces are still there. They're just put together differently. Last law for a while is the law of multiple proportions. The law of multiple proportions is talking about compounds. And if we have two elements, that those two elements can be put together in multiple ways to make up different compounds. So I'm going to stick with my carbon and my oxygen. So CO2 is carbon dioxide. It's in the air that we're breathing right now. Plants use it up and turn it into oxygen. Carbon monoxide, CO, is another compound made up of carbon and oxygen. Those are two different pure substances. They have two different names. They have two different sets of properties. But I've got two elements that make up more than one compound. So in this statement, it says A and B. We could pretend it to be C and O. Okay, so let's take the first compound, carbon dioxide. If I took carbon dioxide and I measured how many grams of carbon are inside of it, and how many grams of oxygen are inside of it, and then made a ratio from that, like took grams of carbon divided by grams of oxygen. Okay. Then I take carbon monoxide, CO, and measure out grams of carbon and grams of oxygen, and then take grams of carbon divided by grams of oxygen and get a ratio out of that. And if I were to compare the ratio of carbon to oxygen in carbon dioxide to the ratio of carbon and oxygen to carbon monoxide, those two I would be able to make a small whole number ratio out of those. So it might be that one of them is 1.5 and one of them is 3. Well, isn't that the same as like 1 to 2? Like we could divide that down to whole numbers. The good news is, well, I don't know if this is good news for you. It's good news for me, I think. This is the hardest one just to read and understand. The other two, maybe not so bad. This one, there's a homework question that helps walk you through actually doing this. And I think that will really, really, really help you with this law of multiple proportions. Okay, so give that a shot. Absolutely let me know if you have questions. But I would try it first. For me, when I was first learning this, I had to sit down and do it, and that's exactly what this homework question is. The last thing on here is just, so now that we've talked about these things, atoms are the smallest particle of an element that retain their chemical identity of that element. So there are things smaller than atoms. We're going to talk about them in this chapter. But if you break something down to smaller than an atom, we're not going to be able to identify what element it is. We need to be looking at a whole atom in order to represent what it is made of. Okay, so now we're to the history of the atom part. So there are going to be several scientists that I'm going to mention. As we go through this, what you need to get out of this portion of the chapter is you do need to know the scientist's name, and really what you need to know is their last name. Okay, you need to know their last name, and you need to know what it is that they contributed to understanding atoms. Okay, like what was it that they did? You don't really need to know what their country of origin or what year this happened or when they got married or their favorite color. Like, I don't know. Know their last name, know what they did to help the understanding of an atom. And we do need to know the order in which these discoveries happened. So Dalton is our first scientist. So he's the first one to make a contribution to understanding atoms. Okay. He developed his idea were these 4 postulates, these 4 statements. Okay. He's also the first one that came up with the idea of atoms. So he's like the father of atoms. And then he has these 4 postulates. So what you're going to need to know out of this is he was the first one to come up with the idea of an atom. His name is Dalton, and we need to know these 4 postulates. So we're going to start at the top. Postulate number 1. Atoms are made up of tiny, indivisible, indestructible particles, and elements are made up of atoms. So atoms are tiny. Yup. They're indivisible. You can't break them, or they're indivisible. There's nothing smaller than them. They're not made up of anything inside. They're solid like a billiard ball. Okay. They're indestructible. You can't destroy them. There's nothing smaller than them. Okay. And then elements are made up of atoms. That's a statement. Bam. Okay. Postulate number 2. All atoms of a given element, so all atoms of gold, are identical to each other in their mass and their properties. And there's a second part, that all atoms of one element are different from atoms of other elements. So every atom of gold looks different than every atom of silver. So he's saying every atom of silver is exactly the same, and every atom of silver is different than every atom of gold. He didn't explain how or why, but just that they are. Okay. Postulate 3. Atoms of an element are not changed into atoms of a different element by chemical reactions. Atoms are neither created nor destroyed in chemical reactions. Dalton's third postulate is basically the law of conservation of mass. So good news is you already know it, but you still have to know that Dalton said that. And then the fourth postulate is that compounds are made when we take atoms of more than one element and we combine them together. The good news is this is basically a definition of a compound, and we talked about this in chapter 1. So these are Dalton's 4 postulates. I think it's ridiculously impressive what he did, because he did this before we had the technology that we have now. So he did experiments in the macroscopic, like big enough that he could see the results, and then tried to theorize on the microscopic level. Now, not all 4 of his postulates survived technology increasing and better experiments, but the fact that any of the things that he said were actually accurate is still just amazing to me. Okay, so what we're going to look at now are some of the experiments that came after Dalton that progressed the understanding of atoms. And again, it's not that Dalton was bad, it's that he didn't have the technology to work with that these later scientists did. So there are 3 experiments in our textbook. We're going to talk about 2 of them, the cathode ray experiment and the oil drop experiment. So the cathode ray experiment was done by J.J. Thomson. So Thomson is his last name. It happened, again, you don't have to know these years, but Dalton's stuff happened early 1800s, like 1809, and we're talking like 90 years later. Okay, so it was a ways later before this happened. Dalton was looking at cathode rays, and cathode rays, as far as we're concerned, are just streams like rays of negatively charged particles. Okay, and so that's like that red line in this picture are the cathode rays. Okay, so then the thing that has the N and the S is a magnet. So what happened was when he threw his cathode rays through this magnetic field, it turned out that some of them were attracted to the positive end of the magnet, some of them were attracted toward the negative end of magnet, and some of them were not attracted to anything and just kept going straight. That's why we see these 3 electron paths in terms of how they respond to negatively charged things. And so we saw things that were negatively charged that are inside of atoms. And so Thomson is the one that discovered electrons. Okay, he's the one that said, okay, there has to be something negatively charged inside of the atom because it repels from the negative charged piece up here. So here's another, we got negative and positive here going on. And so we saw negative pieces being repelled from the negative and being attracted towards the positive. There was a lot more behind the scenes going on here. But as far as we're concerned, Thomson discovered electrons and that electrons live inside of an atom. So what happened was we just destroyed one of Dalton's statements. Dalton's first statement that says atoms are tiny. Well, they're still tiny. That they're indivisible, so they can be broken down into smaller pieces, and one of those smaller pieces are electrons. So that first statement of Dalton kind of got scrapped here. Okay, the Millikan oil drop experiment. This is actually, I have his name on there, but you don't really need to know it in this case. Actually just built on what Thomson did and got us more information about an electron. So at this point, we already knew about electrons. And so what this experiment did was we had this positively charged plate and a negatively charged plate. And then these little red dots are little sprays of oil. So just think like an aerosol, like you spritz the oil and it spritzed. Each of those are a little tiny dot of oil. And then we added... Well, I guess I didn't explain it anymore. We added electrons to those. So we made those little pieces of oil covered in electrons so they're negatively charged. And then they varied the positive and negative charge of these plates and measured how fast they fell from the top to the bottom based on the charge. The end of the day, what they got out of this was the charge to mass ratio, which gave us the actual charge on an electron. Now, most people, when they hear this, they're like, well, electrons are negative. Duh. So charge is a measurement that you can make. And we call electrons a -1 charge because that makes our life easier. But charge it's not actually -1. That's just our way of simplifying it. So they got the actual number for the charge. So once this happened, Dalton's 4 postulates kind of got screwed over. So I know it only really destroyed one of them, but that's enough for an entire model to not be considered accurate anymore because part of it's wrong. So Thomson, the guy that did this, came up with his own model of the atom. So here's our second scientist, Thomson. Okay, and he came after Dalton. And his contribution, well, again, he discovered an electron, so he had to figure out, so how does that electron, it's inside of the atom, how does that work? So his is called the Plum pudding model, and his has a picture to go with it. So Dalton does not have a picture, he just has 4 postulates. Dalton didn't have a picture because he didn't think there was anything going on with an atom other than it's a sphere. Like it's just a solid ball, and so he had no picture to draw. So Thomson's Plum pudding model looks like this. In my head, I call this the chocolate chip cookie model. So chocolate chip cookie. I'm super classy. So in this, to me, these are the electrons, okay? And they're the chocolate chips in the chocolate chip cookie. And the pink stuff is some positively charged goo, okay? So that would be the cookie dough. So in Thomson's model of the atom, if you could draw me this picture, like here's the atom. Here's, oh, this is beautiful. And all of these are electrons, and this other stuff is positively charged gooey energy things. then you know the Thomson model of an atom. He's saying that electrons are spread throughout an atom, but there had to be positively charged stuff inside of the atom as well because an atom was overall neutral. But at this point, there was no name or information about that positively charged stuff. It was just implied it had to be there. And there's Thomson's model of the atom. Okay. So last scientist's name for you to know is the Rutherford model of the atom. So Rutherford is our third scientist. Now, there are actually 2 more models of an atom after this one, but we're not going to see those until later in the semester. So for right now, Rutherford model of the atom is our final model of the atom. Okay, so Rutherford was doing an experiment on completely different things and inadvertently learned something about an atom. And this is how science works a lot. You're trying to learn something. You're trying to prove something. You're like, oh, I got this amazing idea. It's going to be wonderful. I'm going to go in the lab and I'm going to prove it. And then you end up not learning anything at all about what you were trying to learn about. And instead, you found something different. That's what science is all about. Okay, so in this experiment, this right here, which looks like a Cheez-It, is actually a piece of gold foil. So think aluminum foil, but way more expensive because it's made out of gold. And this is just a source, and then these red lines in this are alpha particles. Don't super worry about what they are, but they're little tiny, they're like, well, I don't have the words to even explain them. They're very, very small things, okay? And what they expect, and then this ring around it is a way to measure where the alpha particles go, okay? So they threw all these alpha particles at this gold foil, and what Rutherford expected to happen was all of the alpha particles to go right through it, for all of them to just go through the gold foil, because these alpha particles are smaller than gold atoms. And so they expected, based on the Thomson model of the atom, electrons they learned were negative charge. They also knew that they were super duper tiny. So that's what came out of the oil drop experiment. I think I forgot to say that, that electrons are very, very, very small compared to an atom. So they knew electrons are super tiny. These alpha particles are bigger than electrons, but they're smaller than gold atoms. So Rutherford expected the atoms to go straight through, or the alpha particles to go straight through the gold atoms and all end up on the other side. But what happened was most of them did. Like 98, 99% of them went straight through, but a couple of them bounced off. Okay, and a couple of them went straight back, and that was unexpected. And nothing about the plum pudding / chocolate chip model of the atom explained why that happened. Okay, so most of them went straight through, but a few of them were deflected and went at weird random angles. Okay, so Rutherford had to come up with okay, so he didn't expect that to happen, but it did happen. So why did that happen? So that was then what he did next. And so this is what came out of his experiments. Most of the mass in an atom is in this very tiny, very positively charged thing called a nucleus. Okay, the nucleus is really tiny and it's got positive pieces in it. Most of an atom is mostly empty space, intermittently filled with these tiny, tiny electrons. Okay, and so the way he explained that was all the alpha particles that went through the mostly empty space that had the electrons in it, those are the 98 to 99% of them that went straight through. That 1 to 2% of them that happened to smash into the nucleus, those were the ones that were deflected. The nucleus is super dense. It's very tiny. Okay, so when these alpha particles hit it, although the alpha particles were bigger, actually in this case they were smaller than the nucleus, they bounced off. Okay, so that's the scattering came from when the alpha particles hit the nucleus, but it's just the nucleus is really tiny. So this was a picture trying to explain that, where this orange thing is supposed to represent the nucleus, and then the kind of tan stuff around it is where all the empty space in the atoms are. Now, I'm not a super big fan of this in terms of an atom, so I'm going to say this is my atom. The nucleus would be super tiny. I'm going to give you an explanation of the relationship between a nucleus and an atom here in a second. But these purple things are the alpha particles. So went straight through, went straight through, went straight through, went straight through. Only the ones that happened to hit the nucleus made weird angles. But remember, only about 1% of them did. So this nucleus had to be super duper tiny. Okay. So in terms of size, oh, crap, what's it called now? I always forget what it's called. Where the Rams used to play, and I guess where the Battlehawks played for a very short amount of time, the Edward Jones Dome, but now it's something else. if I were saying that that was an atom, if I were to take a marble and throw it in the middle of the field, that would be the nucleus. That's the relative size from a nucleus to an atom. So that's why most of these alpha particles went straight on through, because probability-wise, you're not going to hit that marble very often. Okay, so we have some new words. We already knew an electron. Okay, we learned that from Thomson, but a proton, that's the positively charged piece that Rutherford said was in the nucleus. Now, it came a little bit later, but he realized there was a third piece to this, and that's the neutron. The neutron also is inside the nucleus, and he figured that out because there was mass missing. He knew the number of protons, he knew the number of electrons, and when you add up those pieces, it didn't make the mass of the total atom, so there was a third piece. So protons and neutrons are in the nucleus. Electrons are negatively charged, and they are floating around outside of the nucleus. And protons and neutrons are about the same size, and electrons are significantly smaller, like 1,200 times smaller than protons and neutrons. So that's why the nucleus is super duper dense. Okay. That number right there, the 1.602 times 10 to the negative 13th capital C, that capital C stands for Coulomb, and that's the actual charge on a proton and the actual charge on an electron. The electron just has a negative number. Okay, so when we're talking about atoms, I can't go pick up one atom and go plop it on the balance and measure its mass. Balances cannot measure that small of a mass. So they made up a new unit for measuring instead of grams or kilograms or pounds. Those are too big for measuring an atom. So very originally, they titled it atomic mass units, the mass unit when you're measuring an atom. So AMUs, okay? It's really, really tiny unit because atoms are really, 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 really tiny. So that's just the unit factor right there between AMUs and grams. I would always provide you that if you were to need it. But we're going to be talking about atomic mass units in Chapter 2 because we're focusing on atoms. Okay, so we're thinking of them on the tiny, tiny scale, like the scale that you cannot see with your eyeballs. So if we're thinking about atoms on that scale, most atoms have a diameter, so how wide they are. So I think they're spheres, they're like balls. Their diameters are between 100 and 500 picometers, or 1 times 10 to the negative 10th meters and 5 times 10 to the negative 10th meters, so they're super duper tiny. When we're talking about the size of an atom, sometimes this unit, an A with a degree sign on top, shows up. It's not a metric unit, but it still shows up sometimes. It's called an angstrom, and that's the unit factor for it. You will not have to calculate with that for the most part, but I wanted to point it out because sometimes you see it in the textbook and you absolutely see it if you look online. Okay. So that's the end of our first video.